In an insulator, okay, the energy gap between the highest level of the valence band and the lowest level or lowest energy of the conduction band, this is quite large. Fine. Quite large in the sense, how much is it? Much more than 3 electron volts. In conductors, there is practically no energy, there is almost no energy gap between valence band and conduction band. In most cases, they even overlap. So there the energy gap is zero. In case of insulators, the energy gap is small. It is approximately from 0.2 to 3.0 electron volts. Last class, I think I told it's an average of 3 electron volts. It's not an average of 3 electron volts. The highest energy gap for it to be called a semiconductor is 3 electron volts. So it will be less than 3. Fine. And these are the different types of semiconductors. Intrinsic. In intrinsic semiconductors, what happens? Whenever an electron leaves from a valence band and enters into the conduction band, a hole will be left behind. So you will find something called electron hole pairs. Okay. And in intrinsic semiconductors, how many ever electrons leave the valence band and jump into the conduction band, those many holes will be created. So concentration of electrons will be equal to concentration of holes in intrinsic semiconductors. Okay. Next, if you consider a p-type semiconductor, right? Silicon, for example, silicon doped with aluminum, it will have more number of holes compared to the conduction electrons. Because, see, the intrinsically created electron hole pairs will anyway be there. In addition, you will have extra holes. So the concentration of holes will be more than the concentration of electrons. And there's one more point you need to keep in mind. When you dope it this way, okay, with a trivalent impurity and make it a p-type semiconductor, these extra holes that are created, these new extra holes that are created, they're ready to accept electrons, right? Now, these intrinsically created electron hole pairs that are there, basically, how are they formed? When a valence electron jumps into the conduction band, that intrinsic electron hole pair forms. Now, this conduction electron can go and fill this hole. Okay. Basically, in an intrinsic semiconductor, what happens? Uh, Very rarely you will see electron hole pairs getting created like this. Okay. So this conduction electron that is there, once it moves away from that place, it won't immediately find a hole to settle down in. Okay. But in a p-type semiconductor, what you are doing is you are creating a lot of extra holes. So basically you are creating a lot of extra spaces where the electron can settle. This electron which moved away can later settle down somewhere else. Okay. So you are giving it many spots which are available for it to settle down. So what happens? The conduction electrons, which are intrinsically formed, can go and fill these holes which are extrinsically formed or which are formed by the impurity. So as a result, what will happen? The conduction electron concentration will decrease compared to what? Compared to intrinsic one. Okay, intrinsically some electron hole pairs will get created. No, those electrons will go and settle down in the newly created holes. So that electron concentration will decrease, hole concentration will dominate. Okay. Now, where did these extra holes come from? They came from the impurity that you added. Fine. So when you add impurity, what you are doing is you are decreasing the opposite type of the opposite charge carrier concentration. For example, if you are creating extra holes, you are decreasing the electron concentration and thereby increasing the hole concentration. Okay. So the intrinsically created electrons and holes that are there, they have a certain concentration. We call it as Ni. Okay, concentration of intrinsic charge carriers. Now, when you dope the semiconductor, suppose you create an extra hole like in p-type, So that extra hole reduces the conduction electron concentration because these holes accept those electrons. Fine. So electron concentration is decreasing, hole concentration is increasing. But the product of concentrations, Ne multiplied with NH, remains the same as in the intrinsic semiconductor, almost the same. So in the intrinsic semiconductor, concentration of electrons was equal to concentration of holes, which is what we called as Ni. So if you multiply them, Ne multiplied with NH, you get Ni squared. Even in an extrinsic semiconductor, even after doping, the product of electron hole concentrations will be equal to Ni square itself, whatever it was in the original intrinsic semiconductor. Okay. Now you may ask, or let me just clarify once again, when we are doping, we are adding extra charge carriers. How can the product still be the same as the original uh, intrinsic semiconductor? As I said, when you add extra charge carriers, for example, holes, the existing electron concentration will decrease. So Ne decreases, NH increases, the product remains the same. Suppose you add a pentavalent impurity, okay, and make it an N-type semiconductor. When you add a pentavalent impurity, what you're doing is you are adding extra electrons, extra conduction electrons. Okay. The intrinsically generated electron hole pairs are already there. Now you are adding extra conduction electrons. What those conduction electrons can do is they can fill the intrinsic holes. So you are increasing the electron concentration, conduction electron concentration by doping it. But that will decrease the hole concentration and the product Ne into NH will still remain the same, and it will be Ni square, which was the square of intrinsic charge carrier concentration. Okay, so this is an important equation, and you need to know that doping does not only increase the concentration of charge carriers, it also decreases the concentration of the opposite charge carriers. Okay, so if you are adding extra holes, it means you are decreasing conduction electron concentration. If you are adding extra electrons, it means you are decreasing hole concentration. Okay, that process also needs to be remembered. Fine. Let's solve one problem based on this. Just a moment. Right. This question is from your textbook itself, but they do ask questions like this in entrance exams. Very similar questions. Now understand what the question is saying. Suppose a pure silicon crystal. Okay. Pure silicon is an intrinsic semiconductor. Fine. So in an intrinsic semiconductor, they are saying it has 5 into 10 power 8 atoms per meter cube. So they have given you the density of, or I can say atomic density. How many atoms are there per unit volume? 5 into 10 power 28. Okay. It is doped by 1 ppm. Rishi, can you tell the full form of ppm?
Parts per million, sir.
Parts per million. Correct. That means one uh, dopant atom per million. Million is 10 power 6. Okay. Silicon atoms. So you are indirectly given the concentration of the dopant. And it is doped by pentavalent arsenic. They have given you the valency of the dopant also. If you dope with pentavalent, what kind of semiconductor does it become? P type or N type? Silicon valency is 4. Okay. Pentavalent valency will be 5. Means it has more valence electrons. So you are introducing extra electrons. Electrons are negatively charged, then it becomes an N type semiconductor. Okay. So when you dope with pentavalent arsenic, what happens is you are increasing the electron concentration. That's fine, but it will automatically decrease the hole concentration that is already existing. Now they are asking you to calculate the number of electrons and holes. See, not the exact number of electrons and holes per unit volume. Okay, the concentration is what you are expected to calculate. And they have given you Ni. Ni stands for intrinsic charge carrier concentration. Ni is 1.5 into 10 power 16 per meter cube. Means in pure silicon, the concentration of electrons and concentration of holes was 1.5 into 10 power 16 per meter cube. Okay, in pure silicon. So after doping, they are asking you to calculate the concentration of electrons and the concentration of holes. Try this, I'll give you 2 minutes. Yes, Rishi, any answer or where are you stuck?
Sir, I'm not sure. I didn't get it.
Okay. See, you are given Ni, intrinsic charge carrier concentration, and you are asked to calculate Ne and NH after doping. Okay. Now we have only one equation, NeNH is equal to Ni square. Ni is given to us, so we know the right hand side of this equation, but left hand side there are two unknowns. After doping, electron concentration and hole concentration will both change. Okay. Now, observe one thing here. The intrinsic charge carrier concentration, fine, that Ni means before doping, the concentration of conduction electrons or that of holes is just 1.5 into 10 power 16 electrons or holes per meter cube. Okay. Now, we doped it by 1 ppm, right? Now, silicon had 5 into 10 power 28 atoms per meter cube. Now, for every 10 power 6 silicon atoms, you have introduced one arsenic atom. So for these many 5 into 10 power 8 atoms of silicon, how many arsenic atoms are present? If you can find out, you can tell what is the concentration of the dopant first. Okay, let us do that. One atom for 10 power 6, one arsenic atom for every 10 power 6 silicon atoms. So how many arsenic atoms on the whole for 5 into 10 power 28 silicon atoms? That number turns out to be 5 into 10 power 28 divided by 10 power 6. That is 5 into 10 power 22 arsenic atoms per meter cube. Okay, so after doping, this is the concentration of arsenic. Okay, now every arsenic atom will create a will bring with it an extra electron. Okay, because it is pentavalent. That means due to doping, the concentration of electrons, okay, from the dopant is this much, 5 into 10 power 22 per meter cube. Now you look at the existing concentration of charge carriers. Intrinsic charge carrier concentration, it's just 1.5 into 10 power 16. Means those many electrons were there and those many holes were there per meter cube in pure silicon. But once you dope it, arsenic itself is giving you these many conduction electrons per meter cube, 5 into 10 power 22. Existing number is just 10 power 16, but after doping, the new number is, or the extra electrons number is 10 power 22. 10 power 16, 10 power 22, there's a factor of 10 power 6. Okay. So the final electron concentration after doping will be equal, almost equal to that of the dopant itself. Okay. Actually, silicon's existing conduction electrons and arsenic's new conduction electrons have to be clubbed together to get the total number of conduction electrons finally before filling the holes. But adding 10 power 16 and 10 power 22, the result will be close to 10 power 22 only. Fine. Therefore, the final concentration of electrons after doping, after adjustment and all. What adjustment? These extra electrons, they will fill some holes. No, let them fill. Okay. Even then, the final concentration of electrons will approximately be equal to that of arsenic concentration. 5 into 10 power 22 per meter cube. Okay. So this is one thing you need to remember. Once you dope a pure semiconductor, once you dope an intrinsic semiconductor, with a pentavalent impurity, the concentration of electrons will be equal to the concentration of the pentavalent impurity. Okay. And you can think of it the other way also. If you dope silicon with a trivalent impurity brings holes. Okay. So after doping, the concentration of holes will be the concentration of trivalent impurity itself. Fine. So this is how you find out Ne first. So one of the charge carrier concentrations after doping you can find out just by knowing the dopant concentration. Now we know NeNH is equal to Ni square. We got Ne as 5 into 10 power 22 per meter cube multiplied with NH is still unknown, should be approximately equal to Ni square. Ni is 1.5 into 10 power 16. If you square it, 1.5 square is 2.25 into 10 power 16 square is 10 power 32. That's all. From there you can get the whole concentration as well. 2.25 divided by 5 becomes 0.405. Fine. Into 10 power 32 divided by 10 power 22 is 10 power 10. So you can say this is approximately 4 into 10 power 9 per meter cube. That's the concentration of holes. So what you need to remember is once you dope, okay, with a trivalent impurity or a pentavalent impurity, if it's trivalent, you'll be creating holes or holes will dominate. If it's pentavalent, conduction electrons will dominate. Once you dope, uh, suppose you dope with trivalent impurity, the whole concentration will be the impurity concentration. Or if you dope with pentavalent impurity, the electron concentration will be the impurity concentration. Okay, is this clear?
Yes,
And
sir.
with that, you can find out the other charge carriers concentration. Okay, fine. So that is about P-type semiconductor, N-type semiconductor, their charge carrier concentrations and all. So what you can understand from all this is that by doping, you can change the conductivity of a semiconductor. Okay, but that's not the only advantage which semiconductors offer. There is something very interesting that you can do with semiconductors. When you combine a P-type and an N-type semiconductor, fine, you will be forming something called a PN junction. Now, how do we combine P-type and N-type semiconductors? It's not just like bringing them together. Okay, it's not like taking what do you say? One object made of P-type, one object made of N-type, and putting them together. You have to combine them at the atomic level. Okay, so you take one sheet of N-type material or a layer of N-type material. They call it wafer. Okay, a wafer of N-type material, and on that, okay, you add P-type atoms. Okay, so what will happen? You will get a layer or you will get a sheet which consists both P-type and N-type. How do you make something which consists both P-type and N-type? Suppose there is intrinsic silicon. First, you add uh, pentavalent impurity. It becomes N-type. What does that mean? Some of the silicon atoms will be replaced by phosphorus or arsenic. Okay, but still there are other silicon atoms, right? A lot of other silicon atoms. Like in the question that was given to you here, the concentration of arsenic was 1 ppm. Means for every 10 power 6, for every 1 million silicon atoms, there is one arsenic atom. Okay, let it be there. On that, you now add P-type impurity. What is that? A trivalent impurity. Fine. Then what will happen? You will have a semiconductor where there is silicon, there is pentavalent impurity, and there is also trivalent impurity. Okay, that is what you call as a PN junction. Fine. Now, in a P-type semiconductor, hole concentration is more than electron concentration. Okay, so we say in a P-type semiconductors, holes are majority charge carriers. Okay, this term is important, majority charge carriers and minority charge carriers. Okay, in P-type, positively charged holes are the majority charge carriers. And in N-type, negatively charged electrons. See, loosely we call them electrons, but we are referring to conduction electrons. So electrons are the majority charge carriers in n-type. Okay. Now, basically, what happens when you dope with trivalent impurity, you make it p-type. In trivalent impurity, there are these extra holes that are created. These extra holes are ready to accept conduction electrons. Okay. See, conduction electrons will be moving around in the material. Sometimes, due to collisions, some of the conduction electrons will lose energy. So, when they lose energy, they will settle down in a hole. So, holes are ready to accept electrons. And it's quite possible that an electron going nearby the hole fills the hole. On the other hand, if it is doped with pentavalent impurity, you will be having extra conduction electrons, which are freely moving around. And if there are any holes available, they will settle down in those holes. Okay. So this electron hole combination will keep taking place in a semiconductor. Now, if you create a PN junction, means if a p-type region is very close to an n-type region, what happens? This is very interesting. Just a moment. I'll draw a p-type and an n-type region. So yeah, as I said, don't think of it as bringing a p-type semiconductor in contact with an n-type semiconductor. Okay. On the same base, both trivalent and pentavalent impurities are added. Okay. So there will be some regions where trivalent impurity dominates. There will be some regions where pentavalent impurity dominates. Assume those regions are close to each other. Okay. So the left side is the p-type semiconductor. The right side is the n-type semiconductor. Now in p-type semiconductor, okay, there are extra holes. That doesn't mean the p-type is positively charged. Okay. How do you make p-type? You remove silicon and you add a trivalent impurity. So you are removing a neutral atom, adding a neutral atom. We had discussed in the last class, the net charge is zero itself. Okay. The holes are dominating. That doesn't mean there are no electrons. There are electrons. Valence electrons are there. Okay. Same with n-type. N-type as such is neutral. Okay. So p side we show plus signs and n side we show minus signs. That doesn't mean they are positive and negatively charged. It only means there are more holes on the p side compared to electrons. There are more electrons on the n side compared to holes. Okay. Now when a p region and an n region come together, see these electrons that we have shown in red, these are conduction electrons. There are valence electrons as well, but we are showing conduction electrons. Now conduction electrons, their property itself is to roam around the entire material. Okay, they are high energy electrons. Okay. Now, on the same base, if there is a p region and an n region, p region has holes, n region has conduction electrons. Now, those conduction electrons will move to the p side. Why not? They can move around in the entire material, no? Okay. So, on the same base, if p and n regions are both present, these conduction electrons will be free to move around and they will go over to the n side. What basically this happens due to concentration difference. Okay, the conduction electrons will definitely they want to move around. They have the tendency itself is to move around. So some of them will move to the p side as well. Okay, it's all on the same silicon base. So it's possible. So when an electron goes from n side to p side, what will happen on the p side? There are in the p region there are a lot of holes which are ready to accept these conduction electrons. So these conduction electrons, some of them go from n side to p side and fill those holes. Okay, due to their high mobility. Fine. And there is a high concentration of conduction electrons on the n side, and they move over to the p side and fill the holes. So electron hole recombination will occur. As a result, what will happen? One conduction electron will be lost, and one hole also will be lost. Whenever an electron recombines with a hole, one conduction electron and one hole will be lost. Means charge carriers will decrease. Charge carrier concentration will decrease. Okay. Now, holes can also move. We had discussed this in the last class. How do holes move? Basically, hole is a region which is ready to accept an electron. No? So some electrons from the surrounding bonds can come and fill these holes. Then the hole moves to the next bond. Okay, so holes can move on. I mean, holes can also move when surrounding electrons fill the holes. So the hole mobility is there, electron mobility is also there. So at the p-n junction, what happens is electrons move from n side to p side. That will happen. Holes will also move from p side to n side. Okay. And due to that also some electron hole recombination will occur. Okay. Now listen, why does this happen? This happens due to concentration difference. There is more concentration of electrons on the n side. This is the n side. There is more concentration of holes on the p side. Now, you must have heard of this term in chemistry, diffusion, diffusion of gases, particularly, or even liquids. When does diffusion happen, or how does diffusion happen? Diffusion happens from a region of high concentration to a region of low concentration. Now, here, when p and n are present on the same base, electrons, conduction electrons from the n side, simply being higher in concentration, spread themselves out onto the p side. So they are diffusing outwards. Same with holes. Holes being higher in concentration on the p side, they spread themselves to the n side. So from high concentration to low concentration. So there is diffusion of electrons happening. There is diffusion of holes also happening. Now electrons are charge carriers. Holes are also charge carriers. So diffusion of electrons creates a current. Charges are moving. Diffusion of holes also creates a current. This current is called diffusion current. Okay, these terms are very important, and understand the direction of diffusion current. Now, from where to where are electrons going? From the n side to p side. Due to diffusion, electrons go from n side to p side. Now, if an electron goes from n side to p side, electron is negatively charged. Negative charge moving to the left means current flowing to the right. So this results in some current. Okay, electron going from n to p results in a current to the right side from p to n. Okay. Holes go from p side to n side. Holes are positive charge carriers. When positive charge moves to the right, it's like current flowing to the right. So whether it is electron diffusion or hole diffusion, both of them result in a current from p side to n side. That is called the diffusion current. Okay, this term is very important. So simply because of the concentration difference, charge carriers move over from one region to another region. As a result, there will be a current, and that current is called diffusion current. And diffusion current will always be from P to N. Whether it's electrons diffusing or holes diffusing, the current will effectively be from P to N itself. And see, electrons going from N side to P side. N side electrons are majority charge carriers. They are going to the P side. P side holes are majority charge carriers. They are going to the N side. And this movement is what results in diffusion current. So you should remember that diffusion current arises due to the movement of majority charge carriers. Okay, this is a very important thing. So hope you understood this process of diffusion and the current that it results in. Now, electrons from N side, when they move to the P side, they will fill those holes, fill some of the holes on the P side. Holes from the P side, when they move to the N side, they will accept some of those electrons. So as I said, whenever an electron fills a hole, whether it's happening on the p side or on the n side, both electron and hole charge carrier concentration will decrease. Okay. So basically, charge carriers get depleted. Fine. So whenever an electron and a hole recombination occurs, it depletes the charge carrier concentration. Okay. Now initially, p side, n side were neutral. But when electrons go from n to p, when something loses an electron, it becomes positively charged. Okay. So n side after diffusion, or you can say due to diffusion, n side becomes positively charged. Fine. Diffusion of electrons makes it lose negative charge, so it will get positive charge. Diffusion of holes directly makes it gain positive charge. So effectively, n side will become positively charged. And what about p side? P side becomes negatively charged due to diffusion. Electrons are coming to the p side, no? So it gets an excess negative charge. And you can also say holes are going away from the p side. That will also leave excess negative charge. So p will be negatively charged, n will be positively charged. Now, when one side is positively charged, there's a net positive charge on one side and there's a net negative charge on one side, there will be an electric field. Okay. Now, from where to where is electric field usually directed? From positive side to negative side. So, once this electron hole recombination, not recombination also, once diffusion occurs, automatically an electric field will get created at the junction. Okay, just a moment. Yeah. The electric fields generally are directed from positive charge to negative charge. Now, due to diffusion, which side became positively charged? N side became positively charged and P side became negatively charged. And due to diffusion, there is a depletion of charge carriers, right? So some of the electrons which jump from N to P fill some holes on the P side. Some holes which go from P to N accept some electrons on the N side. So there is a depletion of charge carriers that occurs. Let's remove two layers. Okay. So this area which now effectively doesn't have any charge carrier concentration, this area is called a depletion layer or a depletion region. It is depleted of charge carriers. What charge carriers are depleted? Those extrinsic, the ones which are brought in by the dopants, those charge carriers won't appear. Now, intrinsically, means in a pure semiconductor, randomly this electron hole pair formation will keep happening. No, some of the valence electrons occasionally jump into the conduction band. That process will keep taking place. That process keeps taking place in all types of semiconductors. Okay, random electron hole pair formation takes place, random electron hole pair recombination also takes place. That will keep going on. Okay, so even in the depletion region, that will keep happening. Occasionally, you will see some electrons jumping from valence band to conduction band, and you will see some electrons going back from conduction to valence band also. But intrinsic charge carrier concentration is very less. No, after doping, it's the extrinsic charge carriers that dominate. Fine. So the depletion region, you can say effectively doesn't have much charge carrier concentration at all. Okay, that's why we call it depletion region. Fine. Don't say it is totally zero, but it will have negligible amount of charge carrier concentration. Occasionally, some conduction electron may appear. Okay, or a conduction electron and a hole pair may appear. Fine. Now, in the depletion region, okay, now due to diffusion, we have discussed that N side becomes positively charged, P side becomes negatively charged. So, in this depletion region, there will be an electric field. The electric field will be from N side to the P side like this. Why? Because usually electric field is from positive side to negative side. Now, what will this electric field in the depletion region do, or what can it do? Electric field, what can it do? It can exert force on charges. Okay. So this electric field that is formed in the depletion region, as any electric field would, can exert a force on the charges. Now, in this depletion region, suppose occasionally some electron hole creation occurs. Okay, let's say a valence electron jumps into the conduction band. So one electron will get created, one hole will also get created. Now electron is negatively charged, hole is positively charged. What will electric field do to positive charges and negative charges? It will pull electrons or it will pull negative charges in a direction opposite to itself. Okay, suppose randomly some electron hole pairs like this are getting created. So this electric field, which is there in the depletion region, will exert a force on electrons this way. So what it tends to do is it tends to bring back the electrons from p side to n side and will exert a force on the holes this way. Okay. Holes will experience force in the same direction as electric field. Electrons will experience force in the opposite direction to electric field. So the electric field in the depletion region tends to bring electrons back to the n side and push holes back to the p side. Now the movement of charge carriers due to electric field, okay, that process is called drift. Okay, movement of charge carriers due to concentration difference is called diffusion. But movement of charge carriers due to electric field, fine, is called drift. Now, diffusion happens, for example, you take electrons. Okay, just a moment. You consider electrons. Electrons diffuse from n side to p side, but electrons drift from p side to n side. Okay, you can see that clearly. Now, when an electron goes from p side to n side, it's like negative charge going from p to n. If negative charge goes from p to n, it results in a current from n to p. Okay, so it will result in a current flowing this way. And this electric field that is there in the depletion region, it can push holes onto the p side. The holes are positive charge carriers. Positive charge going from n to p results in a current from n to p. Okay, so whether it is electrons that are drifting or holes that are drifting, the result of a drift is a current from n side to p side. And remember, what I mean, which charge carriers undergo this drift? Now, see, this electric field is in the depletion region. In depletion region, extrinsic charge carriers are not there. Those extra holes and electrons that you introduced by adding dopant, they are not there. Occasionally, an electron jumps from hole into the sorry. Occasionally, an electron jumps from valence band into the conduction band. Those are called intrinsic charge carriers. They are there. Okay, and those are the ones which participate in drift process. Okay, those are the ones which move due to this electric field mostly. Okay, so what happens whenever an electron, okay, I should properly show it like this, just a moment. Whenever a conduction electron gets produced on the p side, the electric field will bring it back to the n side. And whenever a hole is generated occasionally, okay, see, you can't say only electrons are generated or only holes are generated. Electrons and holes will both be generated. Okay, whenever an electron leaves a bond, a hole will be created automatically. Okay, so fine. Imagine electron hole pairs like this getting created on the p side and also on the n side. Now, holes will experience force towards the p side only due to this electric field. Fine. So whatever holes are created on the p side will stay there itself. Holes created on the n side will be pushed to the p side. Next, electrons. Electrons, conduction electrons sometimes get generated on both sides. Electrons which are there on the n side will stay there itself because the electric field is pulling electrons to the n side. So they will stay there only. The ones which are generated on the p side will also get pulled to the n side. Okay. So in drift, what happens? Electrons go from p to n. Holes go from n to p. Now, p is called p because holes are dominant on that side. Occasionally, you may find, or very rarely, you will find electrons there, conduction electrons. Drift brings those conduction electrons back to the n side. Okay, so basically, you can understand that drift current is due to minority charge carriers. Okay, if there are any electrons on the p side, they will be brought to the n side. But on the p side, electrons are minority. Okay, p is p because holes are majority. Positively charged holes are majority. So electrons are minority. They will participate in drift. Same uh, with respect to movement of holes from n to p. N side, n is called n because negatively charged electrons are dominating. Hole concentration is very less on the n side. Fine. Or holes are a minority on the inside. They will go from N to P due to drift. So drift current is due to minority charge carriers. Diffusion current is due to majority charge carriers, movement of majority charge carriers. And remember, diffusion happens due to the concentration difference. Drift happens due to the electric field in the depletion region. Okay. Now, in a PN junction or at a PN junction, both these processes will keep happening. You can't stop conduction electrons from moving over to the P side from N to P. Naturally, they will go. And when they go, the electric field will tend to bring them back. So both these forward and backward processes will keep happening. So diffusion current will be there. Drift current will also be there. Okay. And they will be, I mean, why will one current dominate? You can't expect a current to keep flowing through a cross section on its own. No? So when some electrons jump from N to P, the electric field becomes strong enough and brings the electrons back to N. So drift process and diffusion process will keep happening simultaneously. And the net current, okay, how do you calculate net current? Net current is the sum of diffusion and drift currents. Okay, diffusion current is in one direction, drift current is in the opposite direction, and they are of same strength. Therefore, the net current is zero at an unbiased PN junction. What is an unbiased PN junction? Basically, what does bias mean? Being biased to something or someone means favoring them, right? So when you don't favor externally, when you don't favor any of these processes, diffusion or drift, okay, when there's no external agent influencing these, naturally they'll be equal, they'll be balanced. Okay, that is what we call as unbiased PN junction. We are not favoring any of these processes. At such a PN junction, the net current will be zero. Okay, that doesn't mean there is no charge movement at all. You cannot stop movement of electrons altogether. Okay, except at 0 Kelvin. And now we are taking non-zero temperatures only. So electrons will keep moving from N to P and they will keep being brought back from, they'll keep getting brought back from P to N. Okay, so diffusion and drift will both be happening at an unbiased PN junction. Fine. Remember that diffusion happens due to majority charge carriers. Drift happens due to movement of minority charge carriers. Maybe I should mention that. Okay. Diffusion happens due to the concentration difference. Drift happens due to the electric field that is generated in the depletion region. Okay. And why is that region called depletion region? Because electrons and holes have recombined in that region. Okay. So conduction electron concentration will be very less in that region. Hole concentration also will be very less in that region compared to the rest of the material, rest of the P side or rest of the N side. That's why that region is called a depletion region. Okay. Now N side is positively charged effectively after the diffusion process. N side is positively charged, P side is negatively charged. You know there is an electric field. That electric field will be there. Okay. Now electric field generally is from, I mean, is directed from a region of high potential to a region of low potential. So here what should happen? The N side being positively charged will be at a higher potential. P side being negatively charged will be at a lower potential. Okay. So there is a potential difference between the P side and N side in an unbiased PN junction. You can visualize it like this. Drift is happening, diffusion is happening, but there is a potential difference. Now P side is at lower potential. Now in the depletion region, there exists an electric field. When there is electric field, there will be a variation in potential from point to point. So from P side, when you move towards the N side, you will be going from a region of low potential to a region of high potential. Potential increases gradually. like this. And then you reach the N-side potential. It's better to call them P region and N region. It will help you remember that P and N are both formed on the same silicon base. Okay, it's all one semiconductor only, in which on which some regions are P dominant, some regions are N dominant. Okay, I mean some regions are hole dominant, some regions are electron dominant. Okay, so there will be a clear potential difference between these two. Now, electrons, they diffuse from N side to P side due to the charge carrier concentration difference. They diffuse from N to P. Holes diffuse from P to N. So when an electron wants to come, or if an electron has to come from the P side to the N side, it has to overcome this potential difference. Same with the hole also. If an electron wants to go from the P side to N side, it has to overcome this potential difference. Okay. So this delta V is called as the potential barrier. Only those electrons which have energy enough to overcome this barrier will diffuse from N to P. Fine. And same with holes also. If they have sufficient energy to overcome this barrier, only then they can go from one side to the other side. Right. So remember this term also, potential barrier. Basically, it's the potential difference between the P side and the N side. Fine. So this is what happens at an unbiased PN junction. The mechanism is very important. Most of the times they ask direct questions based on what happens at a PN junction. Okay, not even the calculations. You need to know the mechanism. Right. We'll stop it here for now. So what all did we discuss today? What happens to charge carrier concentration due to doping? Okay, that is one thing. NENH is equal to Ni square. Then if you create P region and N region on the same base, okay, you will be creating a PN junction. So what happens at the PN junction we discussed in detail. Next class we will discuss what happens at a biased PN junction. Biasing means what? Favoring one of these processes, either diffusion or drift. If you favor diffusion, it's called forward bias. If you favor drift, it's called reverse bias. Okay, those things we will discuss in the next class. That is also very important. Based on that only, you can explain the working of semiconductor devices. In fact, what happens at a PN junction which is biased is what helps us devise or create new devices, okay, which are called semiconductor devices. And those processes are also very important. We'll discuss that in the next class.